Sixth module is PN sequences. It's a coded sequence of ones and zeros with a few autocorrelation properties, and it's used in spectrum communication. It's generated by a bunch of shift registers with an XOR adder next to it. So the length of the shift registers is given by m, and the length of the PN sequence that you eventually get is given by 2 power m minus 1. So let's say the question is generate a PN for the feedback shift register 3, comma 1. Then the first number in that square bracket is always going to be the length of your shift registers. So the number of shift registers is 3, and the second one is feedback. So what this means is that your feedback is coming from x1 and x3. So you'll see that there is a line drawn from the output of the first flip-flop and the third flip-flop, and that feedback is fed back into the first flip-flop. So the length of the sequence is n equals 2 power m minus 1. So since we've been given m equals 3, then n becomes 7. So then we have 8 levels because we have 3 registers. Now, we don't want to start with an input of 0, 0, 0 because it's always going to end up being the same sequence over and over again. This is known as a catastrophic cycle. So we don't want this. So what happens is, let's consider, for example, a sequence of 1, 0, 0. The bit x1 is going to be replaced by XOR of x1 and x3. So if you notice in the second row, it's the XOR of the x1 and x3 of the previous row. So the first row is 1 and 0 for x1 and x3. The second row is 1 for that XOR term. And the condition for XOR is if there are odd number of ones, then XOR is 1. So the x2 of a particular row is taken from the x1 of the previous one, and the x3 is taken from the x2. So you just diagonally shift each bit to the right by 1. So the next row, for example, so you have 1 and 0 as x1 and x3 in the second row. So for the third row, the XOR bit is going to be 1 because there is an odd number of ones. And then you shift the 1 and 1 to the right. And then eventually you keep doing the same thing. And you have to stop once you reach the eventual original sequence that you've gotten. So again, you can see that your PN sequence then becomes 0, 0, 1, 1, 1, 0, 1. So the principle here is that if there are maybe 4 bits instead of 3, let's say this x1, x2, x3, and x4, then your x1 value is always going to be the XOR of x1 and x4, unless they specify otherwise. So they will ask in the question saying your feedback should be collected from maybe the second and third register. If they say that, then your XOR, your x1 bit should be XOR of x2 and x3. So it really depends on the question. Now, PN sequences have a few properties. The first is the balance properties. So the number of ones is always one more than the number of zeros in the sequence. So if you notice the sequence, we have 4 ones and 3 zeros, and therefore we can verify the balance property. The run property is, well, a run is a consecutive identical set of bits or like ones or zeros. So the total number of runs is given by n plus 1 divided by 2. So for example, if you see 0, 0, 1, 1, 1, 0, 1 sequence, the number of runs with a length 2 is given by r by 2 power k, which is r by 2 square, which is 4, which is 4 by 4, which is 1. So there we can prove that property as well. The third property is the autocorrelation property. So the ACF of a PN sequence is both periodic and binary. So if we want to define it, then it either becomes 1 when k is an integral value of n and minus 1 by n when it's not. So suppose we have C of n, which is minus 1, minus 1, 1, 1, 1, minus 1, 1. You'll notice that this is the um, part where you convert a 0 to a minus 1 and the 1 stay the same. So each 0 gets converted. And then Cn minus 1 is just the RC of 1 is 1 by n summation of Cn minus 1. So Cn minus 2 becomes the next row, and then eventually you calculate with my RC as the summation of the product of all of these. So the next topic is spectrum technique. So it's a means of transmission in which the data of interest occupies a bandwidth in excess of BW to send data. Is accomplished before transmission by using code. Theory again. So the advantage is that it rejects interferences, which means it's useful in military applications or for anti-jamming purposes. There's a direct sequence spectrum diagram right below, where x of t is the product of s and c, y is the sum of x and j, and u is the product of c and y. And eventually you get the final as s plus cj. So let's have there's a quantity given Tc, which is chip duration. Then your processing gain G will be given by Tb by Tc, the ratio of the time periods. The jamming margin is given by Pg divided by Eb by N naught. Usually Pg is just equivalent to N, which is 2 power m by 1. We already know that. So whenever we're asked Pg, then you can just calculate it as N. The probability of error is given as half ERFC of root EB by JTC, where n naught by 2 is equal to JTC by 2. So there's a probability of error for the direct sequence spectrum. So question here which utilizes the substitution of all these formulas. So you'll see that TB is NTC and TC is 100 new seconds. N is 2 power m minus 1 equals 15. PG is TB by TC like we just discussed. Now the second type of spectrum is frequency hop split spectrum. And this is where a carrier hops randomly between frequencies and uses Airy FSK. The diagram here for the detector as well as the modulator. So the way this works is there are two types of frequency hopping. The first is slow. So for each hop, it uses just a singular bit. And in fast frequency hopping, for each symbol transmission, there are multiple bits used by the frequency hopping spectrum. So you see a diagram there for t equals 1, 2, 3, 4, 5, 6. There are jumps across the frequency values across each time period. So the sequence goes F3, F4, F1, F2, F2, F1. Last bit of theory is channelization. So this is basically three types. The first is frequency division multiple access, FDMA, where there's a frequency band that's allocated to users. The second is time division multiple access, where periodic time slots are allocated to users. And the third is code division multiple access, where code is allocated to users. So it's really dependent on what is allocated. So in FDMA, for example, each frequency band up to M is allocated. This is good for stream inputs, but bad for burst traffic. TDMA is a data burst at full bandwidth, so you get one transmission at every time period, and you have one entire cycle. You also have to note that guard bands exist or guard times exist. So this is a gap between each band of frequency or time. So these help prevent interference in FDMA, and they synchronize the waveforms to a common clock in TDMA. This is a modulator demodulator diagram for CDMA as well. The final thing to note is Walsh functions. This is simple. So they help you generate a sequence that maps 0 to -1 and 1 to +1. So start off with a matrix of one element, which is 0, and then you take the general formula, which is Wn, 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 Wn complement. So for Wn equals 0, you want to reconstruct it to twice the size of that matrix, then you have to take W2 as three WNs and one bit complement on the bottom right. So you have 0, 0, 0, and then 1 on the bottom right. And then you want to double that, you want to do the same thing. So 0, 0, 0, 1 on the top left, and then you take the bit complement and you keep on like doubling it as such. So that's pretty much all for this module, PM.